Okay, can you hear me okay? So this is the second Diviner-related talk. So I advance with this. Okay, so it's a little bit loud. Okay, so thermal inertia is kind of a fundamental parameter that is useful for a variety of different investigations in planetary science. And basically, what thermal inertia describes is the tendency of a material to resist changes in temperature. So that's the why the terminology inertia is used. So just as an example, dust and sand tend to have low thermal inertia, and then highly consolidated materials or rocks tend to have very high thermal inertia. So orbital remote sensing measurements of thermal inertia have proved very useful for both doing geology as well as landing site selection. And the kind of type case for this is Mars, where we have these global thermal inertia measurements from instruments like TESS and the Themis instruments. Okay, so Pierre kind of touched on Diviner. We've got these different spectral band passes spanning across the solar and thermal infrared part of the spectrum where the moon emits its infrared radiation. We're in a polar orbit that precesses around the moon, and we build up these maps. Basically, the native resolution of the measurements is approximately 128 pixels per degree. Okay, so how do we get at the thermal inertia? So there's two different types of thermal inertia that I'm going to talk about. Basically, the moon surface is mainly rock-free. We find that the rock abundances on the surface tend to be down around a few percent, typically. And so what you have to do to get at the thermal inertia of the regolith is basically remove the signature of the rocks first. And what's left is the signature of the regolith. So the way that we do this is by taking Diviner nighttime measurements, which have show the contrast in temperatures between the rocks and the regolith. So at night, the rocks show up warm, the regolith is cool. We measure the abundance of the rocks by looking at the emitted radiation in different spectral channels. So the brightness temperature in one channel will be different from that of another channel when there's two or more different temperatures within that measurement pixel. So this is kind of shown here. So you have the warm rock, the cold regolith. That shows up as a brightness temperature difference or a spectral slope in the emitted thermal radiation. We then remove the effects of the rocks, and that leaves behind this regolith temperature, which is shown here. So then using this regolith temperature, we can estimate the thermal inertia of the regolith itself with the rocks removed. So we get both of these different products. We get the rock abundance and the regolith temperature. This is an example of the rock abundance map. This is from Josh Banfield's 2011 JGR paper. This is for Copernicus crater. So obviously around younger craters, we get lots and lots of blocky ejecta that show up warm at night to Diviner. But again, I wanted to point out that basically, even in these very rocky areas, the actual rock abundance is only a few percent. So most of the moon surface is rock-free. Pierre mentioned these really interesting features that we're calling cold spots. So these very fresh craters that actually the LROC team first noticed as being anomalous. They have this kind of fluidized looking ejecta pattern near the crater. This is a very close-up image, and this is what it looks like in Diviner. So in the Diviner nighttime regolith temperature map, you get this huge region of cold material surrounding the fresh impact crater. It extends for hundreds of crater radii. And it turns out that you can estimate the thickness of this material based on its thermal signature. And if you try to put that material back in the crater, it doesn't fit by at least an order of magnitude. And so what we think is going on here is that the impact process is basically disturbing the regolith in situ. Small particles, a cascade of ejecta particles is stirring up and fluffing up the regolith. So those are some of the thermophysical anomalies that we're looking at. So this initial result for the equator is contained in a paper by Ashwin Vasavada that came out in 2012. These basic results still stand. You can look at that paper for more details on the sort of global equatorial average thermophysical properties. But what we found basically is that there were a couple of different models that people have been assuming for what's going on in the subsurface of the lunar regolith. One had this abrupt step function jump at some depth in this is a density profile here. So this model had a fluffy layer on top with a more densified layer beneath it. We found that before Diviner, that was a perfectly good model for fitting the existing thermal data. But with Diviner, we had so many more measurements across the lunar night that we were able to find inconsistencies between that model and the measurements that we had. So what this is showing is that if you instead assume an exponentially increasing density profile with depth, that provides a better match to the Diviner data. The other thing that we can do with Diviner is measure the cooling of the moon during a lunar eclipse. And the reason that this is important is because on the time scale of the lunar diurnal cycle, you're basically probing depths of a few centimeters or up to 10 centimeters or so. And because the depth of penetration of a thermal wave is dependent on its frequency, with this shorter period thermal cycle that occurs during the lunar eclipse, you can actually isolate the properties of the upper few millimeters of the surface. So this just shows kind of an animation of what that looks like for one particular crater. You can see the cooling during the eclipse. It's interesting that this is at a high latitude, but near the equator, during the eclipse, which only lasts a few hours, the moon's surface gets almost as cold as it does during the lunar night. And that shows you just how insulating this upper layer is. So we can fit models to this cooling behavior. And it turns out that to match this cooling, you need a thermal inertia in SI units of about 10. And that's comparable to silica aerogel, which is one of the least dense substances known, basically. So this upper few millimeters of the lunar regolith is extremely, extremely insulating. We also, during the lunar eclipses, we see rocks on the surface, which means that even on that short time scale, there's not an insulating layer of dust on top of the rocks. That means these rocks have to be exposed, at least on the scale of a millimeter or so. If anyone's interested in our best fit parameters, here they are. You can talk to me later. So what does this mean in terms of the variation in thermal inertia over the lunar surface? So the way that we get the thermal inertia is by fitting these nighttime temperature measurements. And what we observe is that basically by adjusting this, what we're calling the H parameter, which is the scale height of the exponential density increase with depth, that's what we use that as a free parameter, and that corresponds to different thermal inertias. So this is the conversion between this H parameter and thermal inertia. Over the range of variations that we see on the lunar surface, that thermal inertia of that upper layer of approximately 10 centimeters varies from something like 50 to 90 in SI units. So it's still very, very fluffy. It's not advanced there yet. Okay, so this is, geez, the colors are really bad, aren't they? So this is an example of thermal inertia for Jackson crater. So the regolith itself near the impact crater is filled with small rocks from the ejecta. And so the areas around these young impact craters tend to have higher thermal inertia. We see a pattern of decreasing thermal inertia with age. So here's some examples. This is Giordano Bruno with an estimated age of about 4 million years. As you progress to older and older craters, the ejecta deposits seem to get fluffier and fluffier. So this is what's happening basically in our model. You've got this regolith profile of density that's proceeding with time to becoming more and more fluffy as the impact gardening process breaks up these fragments into smaller and smaller pieces. So we can actually use this to constrain models of regolith formation. So this is a figure from a paper by Galt, 1974, where they're showing the number, basically the probability of overturning to a given depth as a function of time. So as time goes on, the probability of an impact excavating to some depth becomes greater and greater. And what we can do is we can plot our thermal inertia measurements as a function of crater age. So this is the measured or derived Diviner H parameter value. So higher H parameter is lower thermal inertia. And we plotted just 4 craters here, but we've done this for many more craters as well. And lo and behold, they tend to fall right on this line as predicted by Galt. Basically, the H parameter, or the thermal inertia of the regolith, is a direct measure of the regolith age around these craters, basically. And then with the added benefit of the eclipse cooling, we also have a constraint on even younger material. So this is a more or less global map of the thermal inertia of the lunar regolith. This is the red areas are areas where you do have freshly excavated ejected material, more densified regolith, and then the blue surfaces are the ones that have been processed and hence are older. We can compare this to the optical maturity based on optical spectral measurements. Basically, as the surface becomes more space weathered, the color changes. And we see a good correlation between optical maturity and this thermal inertia map, which again is related to the age of the regolith. Then cold spots, we can map the thickness of those ejected deposits. So for these very fresh craters, we find that this thickness, as a function of distance, tends to follow a 1 over r to the 3/2 power law. And we don't know exactly why. We've tried to come up with various physical models to explain that particular power law fall off with thickness. So far, ballistic sedimentation seems to come the closest, but it doesn't quite fit the 3/2 law. And then finally, some of the pyroclastic deposits tend to have lower thermal inertia than average regolith, and we're still discussing why that would be the case, but one possibility is that if you have more uniform particle sizes as you would in a pyroclastic glass deposit, potentially that would reduce the thermal inertia relative to the case where you have multiple different particle sizes where they can fill the voids between other particles. Okay, so just to summarize, we can get both rock abundance and thermal inertia from the Diviner measurements. It's very uniform over the lunar surface and very low. This model with an exponentially increasing density in the upper few centimeters seems to be consistent with the cooling curves. And then we find that the regolith thermal inertia is correlated with crater age. So as craters age, the ejecta get fluffier. So the global thermal inertia pattern seems to be well correlated with optical maturity, but we're investigating some interesting differences. I mentioned the pyroclastics, and if anyone is interested in getting these thermal inertia maps for any particular region, I'd be happy to produce them. And then finally, we do see some effects of topography, which we're working on removing, and once that's done, we'll probably release these to the PDS. And that's all I had. Thanks.
Thank you. Okay, we have time for questions. Carly wants her question. So, but can maybe you should repeat the question for those that just tuned in from our viewing audience. But we need the microphone. So.
I see you have an answer to the latitudinal
relationship. So the question was, is there any latitudinal difference or latitudinal trend in the thermophysical properties of the lunar regolith? And this is kind of, in a way, it's airing dirty laundry, but we do find some variation in the best fit thermophysical properties with latitude. And that's what's shown here. So the points are the data, and the black lines are model fits using constant thermophysical properties as a function of latitude. And you can see that as we get to higher latitudes, the fit gets worse and worse. And I don't know if this is real, but if it is, this would imply that the regolith is fluffier at higher latitudes. if this is real. And again, these are our best fit models, so the fact that there's a discrepancy means that there's either something wrong with our model or there's actually a trend with latitude.
So that insulate more at the higher latitude.
More insulating at higher latitudes, yeah.
Right? Oh, no, I get to ask a question first. So, okay, so the question I had, this is just a quick one. Harry Hessinger had a paper from a couple years back that suggested that there's some very, very young Mare provinces, maybe as young as a billion years old on the moon. And so I would assume the rock abundance there might be fresher. Is this something that pops out in your data at all?
Absolutely, yeah. Do I have that here? No, I don't have it here. So we actually looked at his actual regions of interest. So he dated different compositional units based on impact cratering. And so we actually pulled out the thermal inertia for each of the different regions of interest, and we see the trends with age, basically. So again, they're getting fluffier, less consolidated as they age, and we see the same trend that he sees. Although we probably would pick the units a little bit differently.
Okay. Carly, is it really fast?
Real fast, yeah.
Okay, then go.
Any comment on swirls?
Yes, so we see no difference within our uncertainties between the swirl, the thermal inertia of the swirl and off swirl. It just looks the same. There's a difference in the temperature, but that's because of the albedo.
And the swirl meaning?
The swirls are these very unusual albedo patterns with a very interesting swirl-like morphology.
They're not physically related to a physical structure.
Well, that was one hypothesis, yes, but based on these data, it seems like they.
Visible structure through a telescope?
Yes.
Swirls is like something we could have a whole session on easily. So, but why don't we maybe in the question period, this is a good, or sorry, coffee period or whatever. That's a good time to discuss that. So let's thank our speaker one more time.